Chapter 5.4 is the review of the ideal gas law. So we've done all of the basic gas laws like just pressure and volume or just volume and temperature. Ideal gas law is the one that combines them all together. So before I talk about the math, I want to make sure that you remember what an ideal gas is. So this is saying that the gas is going to follow the rules of the mathematical equation perfectly. Which for the most part, we can assume that they do that. Any deviation that they have from like a predicted value is always so small that it's usually negligible. And the rules of like what makes an ideal gas are some of the things we talked about a few days ago. We have high kinetic energy, so they're moving really fast. When they collide, they don't lose energy. They have super, super low density, so there's tons of space in between the molecules. And the two new ones that we don't emphasize as much in honors chemistry, one of them is the idea that when molecules are passing each other, there's no attraction. So normally, if you have molecules that are very polar, you're going to have like a momentary attraction between the two molecules. So like if you have two water molecules that are like coming close to each other, the hydrogen and oxygens like each other, we assume that that does not happen in a gas because they have such high kinetic energy and they're moving so fast and they're so far apart that the polarity doesn't make any difference. And then the last one is the idea that the volume of the container is much more significant than the size of the molecule. So what we mean here, like when we say the volume of a gas, what we're really talking about is the size of the chamber that they're in. We're not talking about the size of the actual molecules. And if you think about that, that's very different from when we're talking about liquids and solids. Like if we say like we have 10 milliliters of liquid, we mean literally from the top of that liquid, the surface, to the bottom of the liquid, it is full of water. So we have 10 milliliters of water molecules. But for a gas, if we say we have 2 liters of a gas, we really have like 2 liters of empty space with a bunch of gas molecules floating around in it. And again, that goes back to the super, super crazy low density. So we're going to just assume every time you're given a volume that it doesn't matter that there's molecules in there. We're just going to take it for like this is the amount of space they have to move around. So the gas laws that are combined into the ideal gas law is the indirect relationship between pressure and volume and the direct relationships between volume and moles. So those things combined make the Pivnert equation. Okay, so pressure, volume, moles, temperature. You should remember what those are. We always have to have temperature in the unit of Kelvin. Okay, pressure can be in any of the units as long as it matches the R constant. Volume has to be liters and has to be moles. And your options for R constant, the one that they use the most is the one that matches with atmospheres. So the R constant has all of the units in it. It's got liters, it's got a pressure constant, it's got moles, and it's got Kelvin. So it'll cancel anything out. The other ones that we use a lot are 8.314, which matches with kilopascals. So that would go here. It still has liters, moles, and Kelvin. And then the other one that we used in Honors Chem was 62.4, but in AP we're going to say 3.6, and that one goes with millimeters mercury. So unfortunately, if you get a unit of pressure that's not atmospheres, kPa, or millimeters mercury, you will have to do a conversion for the pressure before you plug it into the equation. Okay, so first example from the chapter, PVNRT. Okay, we've got moles. It does not matter that it's nitrogen gas because it's already in moles, so we don't need to do a conversion. We have atmospheres, and it's already in Kelvin, so again, we don't have to do anything extra. Okay, we are going to plug everything into where it goes in the equation, and don't forget to plug in your R constant. So the questions will never say what the R value is, you just have to remember to use it. I like how my handwriting gets smaller as I go. I always have this idea that everything's going to fit when I start writing things down, and I'll just never learn. Anyway, okay, so we plug in atmospheres, moles. We have the R constant that goes with atmospheres and Kelvin. If we multiply everything on the right and divide by 1.37, our answer will be in liters because that's going to be the unit in the R constant that's left over. And accounting for sig figs, our answer should be 15.9. All right, the next question here steps it up a little bit. First off, we have Celsius, which does not work. And then the second part is PSI. Okay, but the PSI part does not matter right now. So this question tells us volume, tells us moles, tells us temperature. We know we can always look up an R constant. The issue is that we don't have an R constant that directly relates to PSI. So we're just going to have to pick something else, and then we'll have to convert our pressure to PSI when we're done. So first we plug everything in correctly. Don't forget to change temperature to Kelvin. I went ahead and just picked the R value for ATM since that's the most useful one, and also the standard pressure is 1. So you know a conversion is going to be easy because 1 is always going to be one of the numbers on the fraction. So if we solve for pressure, we get 1.63 atmospheres. And our last step, there is 1 atmosphere for every 14.7 psi. So last step is to multiply by 14.7, and our final answer is 23.9 psi, which for a tire is pretty normal. Okay, just one more, I promise. Let's see. So determining the pressure again, but this time it does tell you what your goal is, millimeters mercury. Here's our problem. We've got a couple. Okay, one is we have temperature again. We've got milliliters, we've got grams. We got all kinds of issues in this problem. I'm sorry, guys. I mean, it's AP. You've kind of learned how things are by now. So first things first, this has to be moles. Helium is not in Brinkelhoff, so that means we just need to use 4.00 grams from the periodic table. So first thing I'm going to do is convert 1 mole divided by 4 grams, and we get 0.0333. Okay, other issue. Next issue is milliliters. Because of the R constant having liters in it, we have to use liters. I know you didn't need to use them for the old gas laws, but the R constant changes things. So we need to convert 648 milliliters equals 0.648 liters. So we're going to use that number. And then our last one is the easy one. We have 32 degrees Celsius plus 273.15. 305.15 Kelvin. Okay, so there's our 3 numbers. And then the R value that we're going to use is the one that matches millimeters mercury, since that's what the question asks for. So we've got moles. We picked the R constant that goes with millimeters mercury. We have Kelvin. We've got liters. We want to multiply these 3 and divide by volume. And the final answer for pressure is going to be 977.9. But I think we are stuck with 3 sig figs, so we will round to 978 millimeters mercury.